Today's first session will be chaired by Professor Subhashish Dattagupta from TIFR Center for Interdisciplinary Sciences at Hyderabad. So with this, I invite Professor Dattagupta to chair the session.
Thank you, Bimalendu. In fact, it is a great pleasure for me to introduce Professor Tilman Esslinger from ETH Zurich. He belongs to the quantum optics group in ETH Zurich. So let me introduce him in a chronological order. Actually, he got his PhD in physics from Ludwig Maximilian University of Munich. He was also associated with Max Planck Institute of Quantum Optics, Garching, Germany. As a student, he could do some phenomenal work on demonstrating for the first time sub-recoil laser cooling of rubidium atoms. They also conducted some pioneering work on laser cooling and atom optics in near resonant optical lattices. Those were the days when plasmonics was coming up in a big way. So they could demonstrate using the surface plasmon the reflection of a neutral atomic beam. Okay, that was his kind of PhD or post-PhD work. And from 95 to 2001, he was the group leader. Before that, he was a research assistant at Max Planck Institute for Quantum Optics in Garching. And that is the work I just mentioned, what he did. And 95 to 2001, he was a group leader in the Ted Hansch group at University of Munich. And there, they could have the first demonstration of quantum phase transition between a superfluid and a Mott insulating state. And they could also measure the long-range order in a Bose-Einstein condensate. And of course, some other pioneering work on atom lasers. Now, since 2001, he's a full professor at the Department of Physics, ETH Zurich. And I must say that they have set up a top of the art lab at this ETH Zurich. And this is one of the internationally leading research labs on the field of quantum gases and mesoscopic quantum optics. So they could do some original quantum simulation, pioneering the field of analog quantum simulation by synthetically creating and studying key models of this quantum many-body physics. Okay, they also carried out seminal experiments with quantum gases in optical lattices to explore Fermi-Hubbard physics and beyond, with the first realization of fermionic Mott insulator. That's a truly remarkable feat. And then they could also build a quantum gas analog of the graphene and topological Halden model, as well as the first observation. They had the first observation of quantum magnetism in Fermi-Hubbard model. They realized a driven Fermi-Hubbard model and observed enhancement and sign reversal of magnetic correlations and demonstrated a first step towards a quantum simulation of lattice gas theories. And his group also pioneered the study of Bose-Einstein condensates in cavity QED. He is going to talk more about that today. Used it to provide a link to the physics of cavity optomechanics, and they could also realize the decay quantum phase transitions. Another new line of research this group is following, that is the measurement of conductances in quantum gases, where they observed for the first time quantized conductance in neutral matter. Of course, Professor Esslinger is a recipient of many prizes, honors, and he also owns a patent which he obtained in 2002. He has a US patent on this device and method for generating and manipulating coherent matter waves. And he has given several named lectures. He has visited many places as a distinguished professor. So he was the Ugo Fano lecturer at James Franck Institute, University of Chicago in 2016. He presented the 37th Hanan Rosenthal Memorial Lecture at Yale University in 2011. Of course, he was a senior research visitor at Cable College, Oxford in 2016, and he was a guest professor at University of Innsbruck, Austria in 2001. And he has numerous grants and other input for his lab. So one of the mentionable ones is this ERC Advanced Grant in 2010 as well as in 2017. And to name one of the prizes, which is very important, so he shared the Philip Morris Research Prize with Ted Hansch and this Emmanuel Bloch in 2000. Okay, I'm not mentioning his other achievements and other feats. So he will be talking about this, how BEC meets this cavity quantum electrodynamics. Professor Esslinger, please.
Thank you very much. Thank you very much for this very kind introduction, which let pass some memories of former times on some experiments. In particular, you mentioned the plasmon mirror experiment, which was really quite fun. That was with Matthias Weidemüller. I think he also gives a lecture here. Yeah. I remember it was kind of a very an experiment which we very spontaneously decided to do, and within a few weeks we did that and surprised the community. No, it was really much fun. Yes. Okay, so what I plan to do for these lectures is to focus on one topic, and that's a topic which is a bit exotic in the sense in the community of quantum gases, and that is coupling a quantum gas to an ultra-high finesse cavity. And I think that's also a topic where, well, one does not yet exactly know where it will finally go. So with some topics in quantum gases, there it's very clear, okay, you try with the Fermi-Hubbard, you try to solve the high TC question, or to see what is the ground state of the Fermi-Hubbard model, and then with the Rydberg tweezers, okay, you try to make quantum simulation experiments with gate-based quantum simulations. I think quantum gases in optical cavities, they are not completely settled yet, because you can use them for ultra high finesse, for ultra narrow lasing. That's in Thomson lab, in Gila done. It's used for squeezing, and it's also used to generate long range interactions and dissipative systems. So there is still a lot to come, and I'm myself very curious in which direction the field will go. I would like to ask the students to use the chat. I will try throughout the lecture to follow the chat as well as possible. My goal is to convey you a feeling for the system. When you have a quantum gas or cold gas inside a cavity, and when you say drive it from the side or along the cavity axis, just that you can start to, in a way, develop your own ideas on such systems. That's the goal. And then, so I will give an introduction in these today, and on Monday there will be a bit more about recent research. I would, at the very beginning, I would like to flash this picture here. So that's how one can imagine a quantum gas. So this blue is a little bit the quantum gas, and then the cavity, the red thing could be the vacuum mode of the cavity, and maybe the laser shines into the cavity, could also be from the side. Since you all have heard a set of lectures already, I think it might be quite good if I start with some questions. You have seen here the quantum gas in a cavity, and now one could think about what type of physics could one expect? What do you basically, what do you associate with such a system? So without, you're free to associate whatever. And so I would be very pleased if you share your thoughts on the chat, so that we can have a little bit of a very general discussion. You need to imagine that at the time, for example, when we started, we didn't have a clue what to expect when we put a Bose-Einstein condensate into a cavity. but well, one had some vague ideas, but these vague ideas, maybe you could also share what you associate. And I'll wait a minute or two now, and you can think about it, and I will have a drink here. And also I need one more piece of paper, and I will be back in a minute. So the idea to ask this question at the very beginning is because one cannot say anything wrong, because I have not taught anything. So the association, one can freely associate what one likes to. Okay, wonderful, yes. Extended long-range correlations well beyond the interaction range. Absolutely. So there is, I mean, if you think about atoms, placing them in a cavity or a single atom, what would it be? It would be one way to look at it is it's like a little refractive index, and that will change effectively the cavity length. And so if you have another atom somewhere, it will also feel the first one, even if they are far apart. And that will give rise to long-range correlations. Absolutely, that's very good. Okay, frequency measurement of interaction. Okay, you can due to the scattering of the light field. So if you drive the system, light might be scattered, and that might be scattered at different frequencies, and from that one can conclude on the interaction. Then time periodic excitations, yes, that's we had even at times, I mean, when we did this cavity optomechanical experiment, there we just saw a pulsing in the system and first could not identify what are the frequencies and thought a frequency one needs to understand in an experiment. Finally, we could see that it was a very strongly driven harmonic oscillator. And then here comes also one can form several microclouds and study the interaction between them. Yes, that's I think a very good idea. It has not been done, I think, in that form, but this is surely a direction which is super interesting. And controlled dissipation in some form. I also agree that is a very good point. And the way I look at that is that here, if the dominating dissipation is a cavity mode, then you have a dissipation which is just on a single mode, and that should allow one to understand the role of dissipation very well. And that's something it's indeed ongoing research to understand what is this form of dissipation compared maybe to other dissipation like spontaneous emission. Then by frequency measurement of interactions, I meant transforming the interaction measurement in frequency space, which is much more precise way to measure interactions. Yes, yes, very good, very good. Okay, so that is, I think there is a lot, and one could there are some things one could also associate, kind of general things like light-matter interaction, very strong coupling between light and matter. And one could also look at kind of different regimes. That could be that one is closer to different resonances of the different frequencies, but all that we will now have a look at, and we will start competing strong correlations between light matter and matter. Yeah, that's also interesting. Yes, you can have light matter interaction, and that then competing with matter interaction. Very good. Okay, so let us start. Let me give you an overview how I planned it. And I thought I start briefly with a single atom in a cavity, just, well, that's the simplest system. And then to a bit introduce the formalism. And then the coupled BEC cavity system. And then I will talk about self-organization and the Dicke transition. And then I will come to more recent experiments, supersolids, and also dissipation-induced instabilities. Okay, good. Let's look at, well, there's also literature. I just put a little bit of literature. Of course, you find the literature in the papers. And I mean, there is, of course, this wonderful book, very general, on exploring the quantum by Serge Haroche and Jean-Michel Raymond. This lecture there, I took quite a bit out of our review. There are also other and more recent reviews, but naturally, since I co-wrote this one, I will follow that review. Okay, so let's have a look in what at a single atom in a cavity, and how we write down the Hamiltonian. And the Hamiltonian would there be in three different parts. The HJZ, where JZ stands for James Cummings, and that's simply the atom in cavity. That means the two-level system, the electronic system in the cavity, just the electronic levels and the cavity mode. And then the H mechanical, and that is where we kind of deviate from the approach of Serge Haroche, because Serge Haroche, typically the external degree of freedom plays less of a role in the first round of experiments in cavity QED. So here we look specifically also at the motional degree of freedom, at the kind of the low energy excitations and energy scales, which is the kilohertz scale of the motion. So here that is motion plus trap. And then there is also the term which is the pumping, which means how we can put in energy into the system, that either you can excite the atoms and thereby put energy in the system, or you can drive the cavity mode with for example, a coherent field. So these are the different parts. And now we can here we can see a drawing which shows the geometry of the system and gives a bit more more of a feeling how we should look at the system. And in particular, also we see here that we have our cavity decay rate kappa. Well, we will write it down in a second. Throughout most of the lecture, we will have the x-axis as the axis along the cavity. And what we also see here are the two possible pumps. There is a pump from the side that would be a laser field that drives the atoms, that drives the transition of the atoms, and that we will look at less because we cannot look at everything. We have limited time, but in principle, of course, you can pump the cavity with a laser field and drive a field in this cavity. And the cavity mode that is shown here, and that is given by f of r. This cavity mode is, of course, a Gaussian mode, but we will not always take into account the Gaussian character. We might often just consider it as a standing wave and not take the Gaussian into account. Yet, if one wants to precisely calculate something, one has to do that. And G, that is the coupling, the single photon Rabi frequency. So that's the coupling between the atom and the cavity mode. Okay, so let's maybe get precise on our different symbols. So A dagger, that is the photon creation. And maybe it's also important to realize that even if there is no field in the cavity, the vacuum still has the mode structure which is determined by the cavity mirrors. And then here omega c, that is the resonance frequency of the cavity. Of course, the cavity has several resonance frequencies. So they are, in our case, fairly far apart. But what we mean here is the relevant resonance of the cavity. And that will be omega c. And we assume that the other ones, the other resonances, are not playing a role. Okay, and f of r, as I said, that is the cavity mode function. And e.g. a standing wave, then we have f of r equals cosine kx. Okay. And then we have G, that is the single photon Rabi frequency. And there we see that depends, for example, on the mode volume. So the smaller the mode volume is, the stronger the coupling. And kappa is the cavity field decay rate. Okay, so there are questions. Let me have a look. Does the size of the cavity affect the spectrum of the two-level system? Of the coupled system, yes, we get we have a Jaynes-Cummings type of situation. So there is a splitting simply due to the vacuum system. And then De Martini's experiment in 1988 used lambda over 2 lambda cavities to lower the mode volume and maximize the atom field interaction. Is there an equivalent in, so how transverse modes affect the coupling? Okay, so in the end, I mean, experimentally, it is to get a strong coupling, you want to have a very small mode volume, because then you get your coupling large. So the dipole is fixed. Your frequency you cannot change, and epsilon 0 also not. What you can also change is, of course, you don't want to have a too large cavity decay. But the cavity decay comes into play as you need to compare it to your single photon Rabi frequency. So in practice, you want to build a small mirror. And transverse modes, how do they affect the coupling? In the end, I mean, what is happening in the cavity, that the mode densities are shifted towards the resonances. In that sense, you can calculate for your single mode, your mode of interest, the coupling. But if you have one mode resonant, if you, by putting mirrors, you of course change the mode structure of the vacuum. In that sense, a higher mode also affects the lower mode, because you still have to get your full basis or with the given boundary conditions. Okay, so let's now be very pragmatical. How can such a cavity be built? And these are the pieces shown from which we built our cavity in our first set of cavities. And the mirrors are these little tiny mirrors. I think they are, I mean, this is a 1 franc coin. So I think they have a diameter of 3 millimeters. And this is the holder, which is having a little pressure it will hold a little bit pressure in this direction. As you can see, that is for that purpose, here is a groove. And then these two pieces are to hold the mirrors, and there is a tiny bit of super glue to fix them here, and I think there is an opening from the side where we can put that in. And then what is not shown is there is a piezo. So there is a piezo tube with let's try to make a drawing of the piezo tube. Maybe it's the color is gray. So the piezo tube has holes from above, has 4 holes and super glue. Yeah. And these pieces go onto the piezo and there, and the whole thing then is clamped in there. And these mirrors are from this special optics company from Boulder. They are quite expensive. One has to buy a whole set of them, because they are kind of the best possible mirrors that you can get. And I mean, there are other, in Jakob Reichel's lab in Paris, for example, what they do, they take, they modify the end of optical fibers and bring them very close together. So also a very neat way to build cavities. Here I should also say the distance between the two mirrors, which sit here then, that is in the final cavity just 180 micrometer. So it's really close. They are really close together, those two. Okay, and there you can, here you can see, there you see the piezo, and the whole cavity sits on a vibration isolation system. And here you see the cavity length, so it's 78 micrometer. Yeah, that's a good question. Did you have to worry too much about stress on the mirrors in mounting them? Yes, we worried, and I think we worried with the glue also. Well, we put the glue, I think, on one point. We thought about that, but I can't remember all the details. And the thing is that finally you have not perfectly symmetric mirrors, so that means you get a little bit of a splitting of the mode, and there is a certain direction of polarization for those two for the two modes that you get. There is a way, if you make it deliberately asymmetric, then you can orient the polarization. So for example, you can grind the mirrors down on one side, and then so that they are no longer round, and then you can deliberately break the symmetry that we did in a second experiment where we have two cavities. So the 178 micrometer is the distance between the mirrors. So that's how much space we have between the mirrors. Okay, and here you see, well, that's a kappa, that's a decay rate of our cavity. And that's the single photon Rabi coupling, and that's decay of the atom. Okay, let's look at the atom. So in our case, it's rubidium, but that doesn't play such a fundamental role. It's just rubidium is very convenient to use and for laser frequencies. Okay, good. And the cavity resonance frequency, we can change, but because of piezo, we can change the length of the piezo. And how did we measure the cavity length? I guess we looked at the spectrum of the cavity, and from that we calculated. Okay, there is a question, the bed on which the cavity is mounted is deliberately structured. Can you elaborate on this? Okay, so we had, the main point is to avoid mechanical vibrations. And that design, that was Tony Oettel, and he looked through the literature of how to avoid mechanical vibrations, and at the same time to have something that is sufficiently vacuum compatible. So those two things were the main point. And what we have is that there are kind of there is a stack, I think, of 3 of these fairly heavy copper blocks, and there are Viton, little Viton spheres which hold them, keep a distance. And I guess there are 3 of those, and then there is another block. I think it's 3 blocks. I mean, it is sufficiently good for us. It's very good, actually, this vibration isolation. I'm not saying that, well, there might be people who do more vibration isolation who know better, who would say, oh, why didn't you do this, that, or that way? So we are not super experts, but we had to become sufficient expert and talk to mechanical engineers to find out how to do it best. And it worked. Thanks for the question. Because indeed, to solve these type of problems that or challenges, that's of course important to make the experiment run. One has to think about that. Okay, so let's look at the atom, and there E is. Let's just go through that. That is excited state, and that is the decay rate. As I said, we use rubidium, and the main reason was that it's fairly easy to create BCs in rubidium, and the lasers are not so expensive, and that is, yeah, it's convenient. And then, okay, this is a raising operator. And one energy scale, as I mentioned before, is will be taken into account the motion of the atoms, and the characteristic energy scale is a recoil frequency. That is a kind of the energy if the atom gets the momentum kick of a single photon. That gives the energy scale, and m is the m is here is the mass. Okay, and then we have a set of frequencies. That's also the cavity one always has an additional frequency. That's a cavity frequency. Okay, we have on the one hand the atomic transition frequency, and we are mostly detuned relatively far compared to the atomic frequency. Mostly, I say, because in some experiment it's different. And then there is the cavity frequency, or the relevant mode of the cavity. And then there is a laser with which we pump the system to get energy into the system, that we call just omega. And so the frequency between pump and atomic transition frequency, so too often we are a few nanometers detuned. And the cavity versus the pump, that's more in the megahertz range, the detuning between, say, 1 and maybe 50 megahertz. Yeah, no, this is a very good question. What makes, exactly, that is what makes the atoms prevent to move outside the cavity. And that is, that will come, it comes in a second. I will come back to that. It pops up in the Hamiltonian, but I will say a few additional words to that. Okay, so we have, okay, so now we have here written down all the frequencies, and we know that usually this is fairly large and this is a bit smaller detuning. Okay, and now we can write down the Jaynes-Cummings Hamiltonian. So that's just the two-level system. And it's written down here already, and it's written down in a rotating frame at omega. So at the pump frequency. And here, these are a bit details that you have a differential AC start shift by auxiliary fields, e.g. optical trap. So you get an effective delta A, and that is influenced by maybe trapping fields. And there we are, of course, at the question that was posed in the chat. And here we have, we said we had these three parts of the Hamiltonian, and the mechanical part includes also the trapping potential. And this trapping is done, for example, by dipole traps, optical dipole traps, or tweezer traps. So you have a strongly focused laser beam, and this laser beam drives the dipole of the atoms. And if it's, for example, ready tuned, then the dipole will experience a force towards maximum intensity of the laser beam. And in this way, we can trap the atoms inside the cavity. Of course, we have to cool them and so forth before. How we bring the atoms into the cavity, I will also tell you. Okay, and then we have, the pump, and there are these two possibilities for the pump. There is a pump which may have a coherent field driving the cavity. So that might be if you shine in, and sometimes we do that, shine in a light field along the cavity axis. And eta would be the driving amplitude. And here it's pumping the atoms, e.g. a standing wave. Perpendicular to cavity. And the cavity axis is, or that would be then H of R would be cosine kz. So perpendicular to the cavity axis, for example. I also realized that there, throughout the lecture, it's not completely consistent what I call omega and what I call eta. I think later there will be also an eta for this instead of an omega. So I please excuse. And mostly we will look at this term. Okay, and if you to take into account dissipation, then you write down the Heisenberg-Liouville equation, and you take the right dissipation Liouville operators. So here I will be only very short. Out of the Hamiltonian, then you need also to get the right Liouville. And there you have to look more into the theory literature. Okay, and now let's look at the dispersive regime. And yeah, let's do okay. Please tell something about incoherent pumping. Okay, you are asking questions. So usually we pump coherently. That's why I'm a bit not surprised about the question, but there is no reason why not incoherently pumping. And one could imagine to excite the atoms to a higher level and then have them decay to intermediate level, a bit like in a laser system. So then it gets much closer to a laser system. So here, I would say here that the main point is taking into account the external degree of freedom of the atoms. Perpendicular direction of standing waves in cavity, how to visualize in a cylindrical cavity. So the cavity, okay, the cavity, okay, here I have a cavity just put here. So this is cavity axis, and then perpendicular, so the pump beam would go here, and here would be a mirror, so it would be in this direction. So then we would have a standing wave field there. Okay, so in one direction. I mean, there are of course several possibilities, but for example, in one. Okay, and let's look at what's called the dispersive regime, and that's a regime again which mostly we're in, where the atomic transition frequency is far away from cavity and pump frequency, which means that the picture that you look at the atoms in the cavity as a little refractive index is good. It gives you a lot of intuition. But if you want to know more, then you take the Hamiltonian that I outlined above, and you take your Liouvillean and then you derive the equations of motion. And then you get an equation of motion for your atomic polarizability, for the atomic polarization, and for the cavity field. And we will further look at that term. So of course you have the atom detuning in it. You again have the mode function. You have the coupling to the light field, and you have the term, the pump term, and you have the here it's the atomic decay term, which we will often neglect. And for the field, you have the cavity decay, and you have the pump of the field. Okay, and if you have a very often used tool is low saturation and large detuning, which is in most of the time the case for the low saturation, and then you can adiabatically eliminate the excited state. Adiabatically of excited state. So basically what it is you say on average your expectation for your sigma z is -1/2. So the atom is practically not excited. And then you can put this into the equation above that value, and then you can solve your equation. Okay. It is, I mean, it is of course a dissipative system, so it is there are non-Hermitian terms, and to take into account you need, well, yeah, I think it's later on. It comes how you treat, how you make sure that your system is can be treated Hermitian. Okay, so we look now, we do the adiabatic elimination, and now we look for steady states of the system. Atoms are driven from transverse direction. Okay, so the omega is unequal 0, and we determine the steady state, and we do that by setting this 0. And this is a position of atom. One has to remind oneself, and that changes slowly. This can also, might also be an operator, okay? If for BC we need to treat it as an operator. And this is -1. And then we get, for example, we get 0 equals I delta A sigma minus G R A plus. No, not an H bar. R minus gamma sigma minus. Okay, and from that we get kind of a steady state value for the atomic polarization, and often we will neglect the gamma, meaning the excited state decay. So that's the atomic decay. And what it means is that the atomic polarization is basically slave to the cavity mode. So the atoms, the internal degree of freedom of the atom, their driven dipole reacts quickly to the cavity field. And the cavity field itself, now we can put that equation to get an equation of the cavity field and solve that equation. And then here we will in particular see that we have an interference term. It is indeed, there is a, for the adiabatic elimination, that's the question here, you need to have decay rates to be very different. Is that always the case? We have a cavity decay rate which is very, which is on the fast scale, so in the megahertz, and the atomic motion in the kilohertz. But it can also be, you can construct experiments where this is not necessarily the case. For example, in Andreas Hemmerich's experiment in Hamburg, there he has a longer cavity with a larger photon lifetime in the cavity. And then you may not be able to do the this elimination. So and you have a kind of, there is a time lag between field and atoms. So it is, I think, this extremely good question, because one needs to be careful, always careful when the simplification and approximation that one does, when they are really true. When one gets used to them, well, when one starts with doing an experiment and looking at the equations, and then one gets used to certain approximations, but then suddenly one might be in a regime where it's not true anymore. And one needs to be aware of that, because otherwise one might go in a wrong direction. So that's, yeah, one has to keep that in mind. Okay, and then, okay, so but here we look at this simple case, which describes, which is valid for a lot of experiments, but not always. And then, I mean, in the end, the dream would, of course, the dream of the whole field. So it would be that you could make even much better cavities than we have. That would be wonderful if you had even much better mirrors and less losses in the glasses, and in the glass. That would completely change the picture. You could do even much more, but we will see. Okay, atoms. Okay, here. Okay, atoms shifts cavity resonance. And we can look at it as a refractive index, which is modulated with cosine square x, refractive. Cosine square kx. Okay. And now let's have a look. Okay. And then what you do is you derive an effective Hamiltonian for the dispersive coupling, which shares basically the same equations of motion. And in this effective Hamiltonian, you can look at the different terms. So this U0, that is G square delta A square plus gamma square. Then you have here, so that is a dispersive shift, and then here it's again this interaction depends on the position where you are. I mean, you need always to keep in mind that the cavity has a mode structure. Even in vacuum, it still has this mode structure. Dispersive interaction depends on atomic position R, and that can be an operator, as I said, can be operator. And the effective, so that's the coupling from the pump from the side, delta A G omega delta square A plus gamma square. And for the case that the detuning is large compared to the atom decay rate, then we have G omega delta A. So here you see a two photon coupling. So that's the vacuum coupling, then our drive coupling, one photon, the other photon, and the detuning. So it's kind of a two photon coupling. One pump photon and one vacuum photon. Okay, so maybe as the last thing concerning the single atom, just, well, which sets the framework for the many atoms. Let's look at the cavity as an atom counter, and that is shown here. So that is, that's why I always said mostly we will look at the far detuned case. Here, it's not far detuned. So here is a situation where you are closely detuned to the atomic resonant with your cavity resonance. So that is this regime. And what you do is to count atoms is that you go to the resonance, to a cavity resonance, and then you detune just a little bit away. You do that all close to the atomic resonance. And then normally you don't see light. You tune, you see light coming through the cavity, and then an atom goes in and it detunes the system out of resonance, and then you see a dip in the detector. And there were in Kimball's lab some time ago, they did the first experiments on that. We used that at some time for an atom laser, which is shown here. You output couple coherent beam of atoms, and then we let it a very, very weak beam, and we counted the atom using a cavity, and then we could make counting statistics by measuring. So here, these are the single transients of the atoms, and we could make counting statistics on that. Okay, so now we will come to coupled BC cavity system, and I think we'll do would suggest a 5-minute break so that I can drink some water, and you can also drink some water or get a cup of coffee. And so let's have a 5 minutes break and then go through the next set of slides.
Okay.
Okay, from my point of view, we could. I had some water to drink, so from my point of view, we can of course continue. Maybe there are some questions. Then of course, it's a good time to ask them. But also, as previously throughout the lectures, I'm happy to take questions. Okay, so then I will continue. And now, of course, comes, so now we completely understand. Now we have a little understanding of the single atom, including external degree of freedom in the cavity. And now let's look at a Bose-Einstein condensate in the cavity. And so one could wonder, I mean, I remember when I started the lab here in Zurich, and we were thinking about putting a Bose-Einstein condensate into a cavity, then Gerhard Rempe, who of course had done much more work on atoms in cavities, on single atoms in cavities, he could not quite understand. I mean, he said, "Oh, why would you want to put a BC into a cavity?" And I told him, well, I think it's interesting. I want to see what's happening. And then later I understood, of course, why he was thinking that doesn't make sense. Because if you look at it just from a quantum information perspective, then of course you want to have the Jaynes-Cummings model, and then you want to look at it, and then you want to have the nonlinearity of a single atom in the atom-light coupling. But at the time, people were, of course, not so much thinking about what else you could do. So we simply did it, and I never regretted it to get into that field, maybe with some a certain naivety. But that's why often I think young researchers, it's good that they just follow their nose and do not feel too much worried about what other people might say, that that's the right or the wrong regime, because it turns out that you can do so much physics, and that you can see, for example, the famous Dicke phase transition. Had I told that to Gerhard Rempe at the time, I think he would have found it a good reason. But of course, at the time, we didn't know that one can see that. So we just moved forward. Okay, so now we understand, of course, the physics much better and what is interesting in the system. So here it's drawn. We have a Bose-Einstein condensate, we imagine, which is here. The nice thing about the Bose-Einstein condensate is that each atom is in exactly the same quantum state. So each atom will couple in the same way with the cavity mode. So here that the particles are identical and that they are in the same state simplifies the understanding dramatically, that you can a strongly interacting atom-light system, that you can actually capture what is happening. Okay, so let's look at the atom. So if we have large detuning, then, okay, now we have learned, I guess, what do we do? Large detuning, then we are purely dispersive. And we can do the adiabatic elimination of the excited state. And one way to look at the system is that you look at as a superfluid refractive index, which is inside the cavity. That's quite a good picture. You have a refractive index medium, that is your Bose-Einstein condensate trapped in the cavity, and that has the properties of the superfluid. Okay, and now what we do now is the atoms, we describe them in by field operator. So we go into a second quantized picture, and we find our single particle Hamiltonian here, for example, single particle Hamiltonian. And H1 is p square over 2m, where p is the momentum of the atom, m the mass. And for classical, that's the classical potential, the trapping potential. Okay. And I hope that, can you let me know whether you can hear me properly? And I'm not sure whether it's on my side of the line or else.
I can hear you.
Yes.
Where can you, maybe if you can hear me, please let me know. Okay, then I know what's going on here. I skipped my backup, that my computer started to back up, and that's why there was, at least on my side, I could not see myself properly. And this second term here, our operator for the atoms in the atomic, there we have the collisional interaction. As you know it from Bose-Einstein condensation. Okay, so we have here the collisional interaction as a U over M. So AS, the scatter. Okay. Transmission is choppy. Is it? I hope. Let's see whether it's now is stopped. It's okay. I wait a minute because I think my computer is now, it for some reason it decided to start a backup, but now it's stopping, so it should soon be fine again. Okay, I hope that it's better. Please let me know if it's not working immediately. If I am robotic, then I hope it's good. Okay. Okay. Here, genau. Now we also, it's kind of now we add the other terms that we have. The cavity, that is basically the same as we had, and now comes the interaction between the atoms and the cavity mode. And now you may briefly think what terms you would fill in here in 1 and 2. So what do you think that the terms, what does needs to go in here and here? And I'm happy on any answer or on the chat. What could be on 1 and what terms? Just bits and bobs of the terms. Atom-atom and atom field interaction. So there is indeed the atom field interaction, and the two parts of the atom field interaction. There is one part, first of all, in higher order photon mediated interaction terms. Very good. So we have one part that is simply kind of a dispersive light shift. So that will be H bar U0, where U0 was our coupling, our atom light coupling term, not the U. The U was the atom-atom coupling. And then we have the mode function and the photon number. That is the light shift term. And here U0 equals G square over delta A, which is defined as the maximum atomic light shift for a single intracavity photon. So that means, okay, you have with a single photon a certain light shift. That's that term. And the second term, that is a scattering, which describes the scattering of the pump wave into the cavity mode. And that goes with our effective coupling, cosine Kx, cosine Kz, A delta A. And that gives a redistribution between pump field, that was this mode cosine Kz, and cavity mode. And the effective, the scaling of it is our two photon pump. That here omega is the Rabi coupling of the drive, the Rabi frequency, and G, the vacuum Rabi coupling. So we have here the two photon vacuum Rabi frequency. Okay, and then here is a bit more written about the dissipation and also that one has to be careful that this Gaussian noise operator that it maintains, it must be constructed that it maintains the commutation relations for the photons. Okay, now let's link what we have done to the usual way how one describes Bose-Einstein condensate and kind of get a mean field description. And we can, well, we can say, okay, why not? Let's start from a point of view of a Bose-Einstein condensate. And we will also see that since we have a global coupling, so all atoms couple to all other atoms, this seems to be suitable for a mean field description, this global coupling. It's actually the essence of the mean field description. Okay, so, and for our field operator, we go to field alpha and fluctuations. The same we do for our atomic field. And then we have square root over the number of condensed atoms, a mode function phi plus fluctuations. And okay, and the terms are described here. And then we can wonder rather generally, what will we get? We should get something like a Gross-Perderevsky equation plus an equation for the field. Okay, so what we should get is Gross-Perderevsky type of equation plus differential equation for alpha of t. And this, okay, so you will see, yeah, here we have our Gross-Perderevsky equation. And now we can see what additional terms we need. And there are two terms. There is one term which is simply takes the fact, reflects the fact that if I have a light field in the cavity, it will give rise to a potential. Now, if I have a light field in the pump, I will have a corresponding periodic potential. So we have U0 alpha t square cosine square k z. And we have in additional, we have a potential that is the interference term. Cosine kx. Okay. Good. And so we have a dynamical potential and the interference term, and I think that should be in our, it should be kx. So there's a dynamical potential plus interference term. Okay, and so we, what time is it? Yeah. Okay. Now we have here kind of the refractive index. I'm a little bit, I think I need to check my X and Y axis. There, I think there might have been between I need to check what the X and Y was in the initial definition. That it should be an X, okay. So it should be an X. Okay, refractive index. And then, okay, and then what you can do with this type of equation, so this should again be a kx square. If you now include the fluctuations in first order, just as you do in the Gauss-Pideevsky equation, then you get the energy spectrum. And this allows you, for example, to see self-organization. Or to look at the phenomenon of self-organization. We will look at the self-organization in an even simpler model, because we argue the main phenomena can be looked at in a non-interacting Bose-Einstein condensate. So if we ignore the atom-atom interactions to first order, so we just say, okay, let's look at if we had a homogeneous Bose gas in a cavity, and that couples to the light field, and then that is enough to get the self-organization and the decay phase transition. And then one can look at it, of course, to get quantitative agreement with the experiment. Then you add the atom-atom interactions. So the general type of equations for these experiments, there you would take into account the atom-atom interactions in the way described just now. But sometimes to getting the key phenomenology in as simple as possible way, you might ignore the atom-atom interactions. And it might also be that, of course, there are regimes, and maybe that's the question, the very last question for today. So in which case can you not ignore or not expect to be able to be allowed to ignore the atom-atom interactions to get a rough picture of what's going on? In what state would you prepare a quantum gas in the cavity, and then that you cannot make the simplification that I say, okay, let's assume a Bose-Einstein condensate without interaction and roughly get the right picture? When would that not be the case? Has anyone a guess or idea when, in which case the atom-atom interactions are an essential part and not a correction? So if someone has an idea, that would, of course, or some suggestion. Strong coupling cavities. Let's see, but would I then I would say, do I always have to have atom interactions? No, but which maybe if you think in which case can I no longer think of a weakly interacting Bose gas, and I can no longer think of, for example, momentum states, extended states. in which I have to do a change a little bit in the experiment, but it's just adding laser beams. And then I get into a regime where I cannot ignore the atom-atom interactions. And it's getting very difficult to describe. Very difficult to describe, but very interesting. In case of multiple photon scattering, I guess so. I guess that's then, of course, the density distribution plays a larger role, and it's getting worse and worse, my description of ignoring the atom-atom interaction. But yeah, I was still thinking about another scenario, kind of combining two fields of cold atoms. If one combines that to the lattice physics. So if I, for example, if I look at a Mott insulator, that I will not be to get the right rough picture if I then ignore the atom-atom interaction. So basically the Mott insulator I would not get, but the Mott insulator will suppress density fluctuations, and that will not make it possible on first sight to get a self-organization, as we will see in a moment. But also it's a typical situation where you cannot ignore atom-atom interactions. But we will see that on Monday in more details. But so if you have some more, we are now at the end of the lecture, but still, if you have questions, I'm more than happy to answer them. So I will still be on the chat here for another few minutes, and I would like to thank you very much for your attention, and yes, and see you on Monday. But as I said, I will be still on the chat now.
Professor Dattagupta, you need to unmute.
Yeah. Okay. So I would first of all, I'd like to thank Professor Esslinger for an excellent lecture. The main beauty of this lecture was really down to earth, and each and every participants really enjoyed this lecture. Okay, and getting into the nitty-gritty and details of each and every step. So I really thank you for that, and hopefully you'll be telling us about some experimental results on Monday, right? That is what you are planning.
Yeah. Yes, okay. Absolutely.
So we'll be definitely looking forward for that. And then thanks for the time being and for this excellent lecture. Thank you. And then there may be some quick questions, 1 or 2 questions, if you would like to take them.
Yeah, so, there is one just came up in a cavity. BEC is interacting with pump beam and boundary conditions due to presence of the cavity. Do these interactions heat up or cool down BEC as pump beam is detuned? Yeah, you can indeed get both regimes. I mean, of course, usually one is more worried that any pumping energy usually heats up, but there are mechanisms, cavity cooling mechanism, where you can actually also cool. To do a really successful cooling that you're colder than before is tricky, but with cooling, to show a successful cooling mechanism, the best thing is always to start hot enough, and then it's much easier to demonstrate a cooling. And that, of course, goes through the literature of different cooling experiments. I learned that during my PhD in one referee, where I realized, well, you need to heat up a bit, and then you can convince the referee. Okay, is there any quantitative change in cavity transmission as the BEC transition is approached? there is not much change because it's effectively the refractive index. So what there might be small changes in the sense that the overlap of the atoms with the cavity mode changes. So so you can look at it as a refractive index. All the atoms, they form a refractive index, and now as you go to the BC transition, the shape of your cloud changes, and that changes your refractive index somewhat, and that will be the effect that you see.
I had one question which I asked right in the beginning. Can you really have an equivalent of a λ/2 cavity, which people were talking about?
What cavity?
λ/2 cavity. What people were talking about early days of cavity QED. λ/2 cavity.
And whether you experimentally you can.
Yes, that's experimentally. Can you achieve that?
I think not obviously.
Of course.
But yeah. I can't give you the answer.
Okay. Thank you so much. So thank you so much for an excellent lecture. Hopefully every participant enjoyed your lecture. We'll be looking forward to your Monday lecture. Thank you.
Yes, and if someone has a question by email, send me an email. I might answer. I cannot promise the answer, but I might come back to it on Monday lecture then. Okay, so wish you all a good afternoon, another set of lectures, and a good weekend. And
have a nice day. Have a nice day. Thank you.
Bye.
Yep.
Thank you, Professor Dattagupta. So next talk is by Professor Jonathan Holm, and the next talk will start at 4:15. So we have 5 minutes now.
Bimalendu, I have another session with somebody else. Okay, so I have to quit. I may not be there for the next lecture. Okay, partly I'll be there. Partly, yeah. Okay. Thank you.
Hello, good morning, Jonathan. Are you around? I guess so.
Yes, I'm here.
Perfect. Okay. So this is Manas here. I would be your host in here, virtual world. Yeah. So I will introduce you, and maybe in 5 minutes time we start. Is that okay for you?
That's fine. Yeah, I'm just trying to get my iPad hooked up because I'm trying a
no worries.
way of presenting today. Yeah. So should I just share my screen now, or?
Oh, you can.
Good. Part of a new experiment today because I'm gradually switching to Mac, and I'm going to try out Keynote on my iPad for presentations today. So let's see how it goes. Yeah.
So experimentalist is switching to Mac. This is not that often happens. Huh?
Well, you know, I was pretty firm Microsoft person actually, but then I bought a laptop last year, which I could write on for lectures, you know, on the screen. And it was an HP laptop. And then sometime around Christmas, it was managing the memory and it was taking all my CPU. So I sort of went into the software, you know, just within Windows and said, turn this off. Yeah. And it managed to encrypt my hard drive and crash the entire hard drive. So I lost everything. Yeah. And at that point, I thought, I don't stick with you guys any longer. If you can make software that does that, I couldn't recover anything, right? Because it had done it in some Intel memory manager type thing. And I think, yeah, anyway. So at that point, they lost me, I'm afraid, yeah.
So you will be talking about the motional state manipulation.
Yes.
I mean, this is your first lecture, and then in the next one, would you continue on this, or would it be a different topic?
No, the next one will be on quantum information, I guess, or quantum physics in penning traps.
In penning traps. So,
yeah.
I see.
But I think, like some of the material in mine, I've been in touch with Christian Roos, and I think he thinks it's good lead into his stuff, if you like. So,
right. So Christian has tomorrow, I think.
Yes, I think that's right. Yeah.
Okay, I guess we are very much on time, so maybe we can kind of slowly start. So I would like to welcome Professor Jonathan Coulomb from ETH Zurich. So we have just had finished one from ETH Zurich, now again. So you can understand the kind of physics going on in ETH. So a little bit of background, Jonathan had his PhD from Oxford and then moved on, or actually carried some postdoc also in Oxford, then moved to NIST, and then joined ETH, and now he's a full professor since 2019. Of course, he has quite a number of fellowships and rewards. The latest one I see is Golden Owl, which is for his teaching. So I believe you will enjoy it. Please go ahead.
Good. Okay. Thanks very much for the introduction. Also, thanks very much for the invitation to talk. It would have been nice, of course, to come and visit you guys as part of this, but this is the modern world. So we fortunately, even in times of crisis, can give these talks remotely. Yeah. So as I explained to our host, your subject of one of my experiments today, this is the first time I give a keynote talk through my Mac, so apologize if we have problems, but I'm an experimentalist. I guess that means that what I know is that experiments always go wrong, yeah, but at the same time, hopefully this one doesn't, because it's been, the groundwork is better prepared. Good. So today's lecture will be on then how to control back to trapped ion systems. So these are these charged atoms in electromagnetic traps. In fact, today will all be electric traps with both static and ponderomotive fields. So this is what we call RF Paul traps. And I think you saw previous introductions to those, and particularly from Stefan Vilic, I saw relevant information for this talk. In fact, the very nature of the trap itself is not a major requirement for this talk. I will mainly call this trap the sort of source of the harmonic oscillator, if you like. And what we want to learn about today is how in trapped ion physics we manipulate that harmonic oscillator with the aim of making interesting quantum mechanical states. And just to start you off, I've drawn on the front cover, if you like, this picture that you see here. So this is actually quantum state, this picture that you see here, and I've made a map of this quantum state where you can think about the axes of this graph as being somehow position and momentum. And this is a plot, if you like, of the probability to find an ion with a particular value of position and momentum. So in particular, wherever you see red points, there is a probability to get a particular position momentum value corresponding to that red point, and the density of the red tells you how high that probability is. But this is a Wigner function, actually, and one of the special things about a Wigner function, which we'll learn in this talk, is that it can take negative values, and that's a key signature, if you like, of a quantum mechanical state. So states that we can make by a classical ensemble of producing something with some random variable probabilistically can only take positive values on this sort of phase space, if you like. And in quantum states, we can take negative values. And that's one key thing that people have been playing with in trapped ion physics, is how to make quantum states of the motional oscillator. So what is the trapped ion mechanical oscillator? Let me just give you the most basic things about it. Why is it an interesting tool? Because it's extremely well isolated from its environment. Okay, so this is a single charge, an atom, trapped in vacuum, ultra high vacuum, by electromagnetic fields. And in our case, there's a combination of a static potential plus some sort of RF potential, which is going to play no role in the rest of this talk. So what do we have with that? We have that the charge is confined at a particular point in space. It seeks the equilibrium point, if you like, but it makes small excursions about that equilibrium. And then in the trapped ion physics, those are extremely well described by a harmonic oscillator potential. So this is the sort of classic harmonic oscillator. We have a spring constant, which is coming from the trap, if you like. So maybe I call it spring just to make it clear, but it's very commonly written in this way of just writing the mass times the frequency squared. Just for convenience, it leaves us with fewer parameters to concentrate on. So all the physics that we're going to deal with today deals with this, these atoms cooled into the quantum mechanical regime. And of course, what you know from your undergraduate quantum mechanics is that at that point, we can write the Hamiltonian in terms of these creation and annihilation operators. And just because we'll use it in future work, I remind you then that the position given by this excursion from equilibrium is written by basically the 0 point motion multiplied by the sum of the creation and annihilation operators that we get. Okay, so that's the sort of course, that's really basic physics, right? This is stuff that has maybe nothing to do with trapped ions themselves. Where it becomes relevant to trapped ions is to think about what the relevant frequencies are, what the size of this motion is, and how that compares to other things that we use to control the system. So in the trapped ion case, then the motion that we talk about, the harmonic oscillator motion, is between about 1 and 10 megahertz. And this depends then on the mass of the ion typically and on the strength of the potentials. So what you will find, sorry, that should not have happened. So what you will find is that for heavy ions, and many people are using, say, ytterbium, right, which has got 171 atomic mass units. You'll find that you have around a 1 megahertz trap frequency. And then the lightest ions that we have are beryllium, which have about 9 atomic mass units. And you will typically find that these are the ions then that have the higher secular frequencies, right? So we can calculate from that, because what we have here is only the mass of the ion and the frequency of the ion. What is the size of the 0 point motion? So that gives you the root mean squared deviation of the ground state wave packet. And typical values you'd see in trapped ion physics are around 10 nanometers, okay? So by contrast with that, sorry, this is more annoying than I thought. By contrast with that, you should think about what could cause this not to be a harmonic oscillator, right? So the thing to always compare with there is some sort of measure of anharmonicity. And there we should think about a length scale that defines the anharmonicity. So you've just been hearing about neutral atoms, right? Neutral atoms, indeed, in Tilman's situation, they're trapped in light fields, right? And the length scale is set by the wavelength of the light. And that means that these are relatively anharmonic because wavelengths of light are a few hundred nanometers, and the 0-point motion, even in a 10 megahertz trap, which is hard for them to achieve, would be 10 nanometers, right? So a factor of 10 or so below. But in an ion trap, the relevant scale is somehow given by the size of the trap. And the very smallest traps that people are using are of order 10 microns or so. I would say more like 50 microns. Let's call it 100 just for the sake of argument. Okay, and you can see that that 100 microns is much, much smaller than the 10 nanometers. Okay, so what does that mean? That means that ion traps are extremely harmonic traps. So this description of having a harmonic oscillator in a trap holds even when you've got quite a highly excited oscillator, which would have many multiples, if you like, of 10 nanometers. It's still going to be much less than 100 microns. So these are very harmonic traps indeed. So what is the interest then in the motional states of trapped ions, and what can we do with them? In a certain sense, this was the entry point for all the quantum control that you've heard about for trapped ions probably in the preceding lectures. A lot of what's happened in terms of progress in quantum computing, progress in quantum simulations, even progress now in spectroscopy, like the quantum logic spectroscopy you saw Stefan talking about, stems from the ability, if you like, to cool the motion of these ions down towards the ground state. Yeah. And those pioneering steps, if you like, started with Doppler cooling of ions in the 1970s, and were really brought into the ground state by Wineland and co-workers, and also people in related groups at the time in Germany, which were able to cool into the quantum ground state. And that was sort of the starting point for a lot of the physics I'll tell you about today. So what do people then do with these mechanical oscillator systems? I think the first place, and the thing you'll see most of today, is that these are somehow a test bed for quantum control. Can you, starting from a pure quantum state, that's the ground state of motion, can you create different quantum states? Can you explore what those quantum states are able to do? And indeed, as you explore this, can you find ways in which that can be propagated into other systems? A second feature, which is important, but a little less important in this talk, is going to be that the Coulomb interaction is what couples ions together. And the Coulomb interaction, if you think about two ions close to each other, I hope you can see me here. So the Coulomb interaction essentially means that one ion pushes on the other, but if one ion moves, then of course it creates a different force acting on the other one, right? So the coupling, this Coulomb interaction, depends on the position of the ion. And of course, the position is an intrinsic feature of this oscillatory motion. So all the quantum gates that you will see, say, Christian Roos talk about, these rely on the fact that you've got these coupled oscillators. So another feature of sort of the general exploration of quantum mechanics, and that's something that you will see in today's talk, if you like, is that as opposed to two-state systems inside an atom, which are related to where an electron sits with respect to the nucleus, an oscillator, the oscillation of this particle, can go to larger and larger amplitudes. And in a certain sense, that means it's a system where, okay, when you have this system in the quantum ground state, you've got 10 nanometer size wave functions. But in principle, one could make bigger and bigger quantum states such that you start to have wave functions that are spanning over microns or more, and starting to come up towards the classical regime. So that's to say that oscillators, as opposed to spins, are systems that you find both in classical physics and in quantum physics. And so in that sense, then, this is an interesting system to explore if you're trying to examine this crossover from classical behavior to quantum behavior. So then some of the things that are both good and bad, right? One is that they're sensitive to their environment, right? So why is that? We've got here a light charge, right? Single atom. So light, because it's a single atom, right? And that means if you have electric fields, that's going to move this atom quite considerably, right? What that means is it's sensitive, and if you can cool down to the ground state, that's sort of getting towards the ultimate sensitivity. It's sensitive to electric fields, and that can be a good thing if you want to sense electric fields. It can also be a bad thing because maybe your ion trap itself produces noisy electric fields, and then you have to deal with those, right? So sensing has been another area where the motional states of trapped ions have been used. And then finally, and I think you maybe saw this in Stefan's talk, the ions are sensitive, and indeed they're sensitive to other effects, right? They're sensitive to other light particles which scatter from them. And one of them that's being used in spectroscopy today is the fact that if you have a neighboring ion which scatters a photon, there's a recoil kick from that, and a single photon can produce a considerable kick on the pair of ions, if you like, which can then be detected. So there you start to be able to see that in spectroscopy of some species that you'd like to get hold of, you only really have to scatter one or a few photons before you can detect that there was some scattering going on. And so then you can compare in this species of interest, was there scattering, was there no scattering? And that's basically the tools of spectroscopy. Okay, so these are sort of the motivating reasons as I see them for studying the motional states of trapped ions. Now what I want to do is to show you the different tools that we use in general to study this. So basically all the physics that I'm going to tell you about is encompassed by something looking, well, not really looking like this. This is my cartoon, of course, but what we have here is a trapped atom, right, sitting somewhere between some gold electrodes, and there's a laser, and I'm going to stick to just laser fields, which is then controlling the motion of that trapped atom. So we can think about what a laser field is, right? It's essentially got an electric field, and it's got an electric field strength, and it's got a certain oscillation frequency, which I'll call omega L, right? It's got some sort of frequency, right? But then we can think, what does it couple to about the atom, right? The electric field, in fact, mainly couples to the internal either dipole or quadrupole moment of the atom, right? So that's not the aspect necessarily that couples to the motion of the atom. But the key thing about a laser field is it also conveys momentum. Photons carry momentum, right? And it's this momentum transfer coupled with the fact that we couple to internal states of the atoms that's going to be key to trapped ion control. So what we have there is then this motion, right? And there are, I just noticed, but we're going to ignore it throughout the rest of the talk, that there are 3 oscillators per ion. And why is that? Because we live in a 3D world. And so there are 3 directions of motion. But all of these are described by a harmonic oscillator, and all the motional directions have different frequencies. So what we're going to do is we're just going to say, okay, the frequencies we choose will only look at one particular oscillator, okay? On top of that, we have internal states of the ion, and I've drawn these as a spin, but this will not necessarily be a spin, right? So not necessary to have a spin. It could be an optical transition, and in fact, I will focus always on optical transitions in the talk that we have today, right? So on top of that, then we have this laser-induced coupling, and we can give it a certain strength, omega, and it's the thing that's going to couple these two together because it couples both to the dipole or quadrupole moments of the internal states, but also the momentum allows it to couple to the oscillator states, right? So here's the momentum, and if you like, here's the quadrupole or dipole moments, right? So internal structure. So if we're to scan the frequency of the laser, that's what you see plotted here, across a resonance of a two-level system in a trapped ion system, then you'll see that there's this strong resonance at the frequency. So that's what I've called omega naught here. I should maybe just label this as omega naught. And then in addition to that, I see resonant behaviors or some sort of resonant excitation that seems to happen at other frequencies here. And these are the frequencies of the motion. So if you like, the frequencies that we find are omega 0 plus omega z, omega 0 plus some omega y, and omega 0 plus omega x. These three being the different types of motion from the 3 dimensions of the ion. Okay. And we also see resonances exactly at the counterparts, which sit at omega 0 minus omega z, etc., if you like. They sit at lower frequencies by emotional frequency than the central frequency. So what are these? These are modulation sidebands. It's like when you have a radio, right? You take a carrier signal at a certain frequency, and then you either amplitude modulate it, or in this particular case, you're phase modulating the radio. And what's happening here is that as the ion oscillates, you can think of the Doppler shift of the laser that's incident on it. The ion oscillates backwards and forwards, and it basically phase modulates the laser as seen in the ion rest frame. Yeah. So let's write down some Hamiltonians. I think you've seen some of this stuff from Didi Leibfried earlier, a few days ago, right? The Hamiltonian that describes the ion interaction, if you like, here's our Rabi frequency again, producing proportional to the field. Here's our creation operator on the internal states. We've got here the laser frequency. And a critical aspect here is that we've got this term here, where I'm already dealing in 1 dimension, and x is the position of the ion. Okay, so under certain conditions, then I can start to expand out this exponential. And in addition to that, and I know you did this with Didi, you can go into an interaction picture with respect to the motion of the ion. And what that really means is that you take, in practice, it's as simple as saying, if I go into an interaction picture with a Hamiltonian of an oscillator, oscillating with frequency omega, which you see here, it means replacing the A operators by A e to the minus I omega t, and replacing the A daggers by an e to the plus I omega t. So if we expand out this exponential, what we see is that there's a term with no time dependence, but then there are these additional terms which have a destruction and a creation operator in and have some additional time dependence in them. So I can think about putting that expansion back into this Hamiltonian. And one of the things that I have to do there is I have to say, how far should I go in my expansion, right? What's the higher order terms here? And what we say, and what we typical regime we work in, is when this parameter eta, which is basically k times the x naught, the 0 point RMS motion of the oscillator, right? When that's much, much less than 1, or at least when eta squared is much, much less than 1, then we say that we can truncate this expansion and get rid of the higher order terms. Yeah. And there's 2 ways of looking at this eta parameter. One is that it compares the RMS wave function extent to the wavelength of light, right? So it's a ratio of those 2. The other one is that the recoil energy of photons that are emitted from the, or of the atom when it emits a photon at a given wavelength, compared to the energy of a quanta of the motion. Yeah. And in our case, and I'm just going to use numbers from calcium here, we have here x naught of around 10 nanometers. We have a wavelength of around 700 nanometers. And you see that when you square the ratio of those 2, indeed, you'll be in a situation where this is much less than 1, and we can justify our approximation. So what should we expect to see? We see again these modulation sidebands. And now, depending on which resonance we're picking out, we get different Hamiltonians. So if we just drive at the direct spin flip frequency, this is this peak in the center here, we see that we've got just a term which acts on the internal state of the atom. If we instead tune to this lower modulation sideband, then the resonant term now is one that's reduced in strength by this factor eta, which is much less than 1, remember, but has interesting terms in the sense that when you excite the spin, then you have to destroy a quanta of the motion. And so that's drawn in this diagram up here. Here we have a situation, right, where if I started in the n equal to 1 motional state, so these are the motional states along the bottom, these are the spin states along the side, then in exciting the atom to the excited state, I have to lose a quanta of motion, right? And so this is driving on this red sideband, and that's why I drive with these diagonal red arrows. And the other situation, which is very common, is that we tune to the other side, to this other resonance, right? And there you see again, it's weaker by this factor eta, but here now when you create quanta in the internal states, you also create them in the motional states. So in a sense, that's this other transition which goes diagonally up from down to up. Okay, so as I say, this is phase modulation essentially of the laser that produces these sidebands. And by picking the frequency of the laser, we can pick out different Hamiltonians. And this allows us then to manipulate the motion of the ion, because some of these Hamiltonians have motional operators in them. So you've already seen from Didi, if you like, how that's used to produce laser cooling. So there we drive this red sideband. So remember, it destroys quanta if we excite the spin. And we add to that a dissipation channel, which means that the spin can decay. What does that do? So a Hamiltonian is always a bidirectional process. It's unitary, right? So it's completely reversible, and it'll produce some sort of cyclic dynamics in this two-state system. But when we have the dissipation, what that does is it's single directional. The spin decays from up to down, but it doesn't decay from down to up. And in our atoms, if you like, we implement that by implementing the Hamiltonians on this transition here at 729 nanometers, but then quenching this transition with an excitation at 854 nanometers to these states here, which are short-lived states. And from there, it decays down into the ground state, but the atom never gets excited from the ground state up to the P3 halves and drops into the other state. So this is the thing that breaks the symmetry, if you like, and tells us that we will pump in one direction. Now, what happens then if we do this cooling, right? So this is the bit of the sequence that I've drawn here, is that there's some cooling. And then we probe again on this same sideband. Okay, so we come after the cooling and we then try and probe this sideband again. And what we'll see is that if we've cooled, we should expect population to arrive down in the ground state here. But in the ground state, there's no possibility to excite the spin again, right? I can put a nice cross on that because it's got nowhere to go. You can't remove any more motion. And that's what you see here. The plot along the bottom here is the time that the cooling is applied for. And you see the ability to excite the sideband. I excite from, if I didn't excite, I would be at 1, if you like, and this goes down, is reduced as I go on with the sideband cooling, and it comes to a steady state where basically I can't excite this sideband anymore. Yeah. Now, how would we draw that if we were to look in phase space? Again, we've got this momentum and position phase space, and you would see that this is oscillator, which if it's really at 0 energy, should sit at 0 amplitude in both position and momentum, right? But you have 0 point motion, and that's the width of this blob that you see here, is the ground state uncertainty. Yeah. Okay, so that's basically sideband cooling. And just to say something about these phase space pictures that's just important in terms of understanding things. So I'm going to plot this Wigner function, right? And I call it a quasi-probability distribution because of the fact it can be negative, right? And you can see that from the following, and maybe I can give you an argument why the negativity is important. One of the important things about this Wigner distribution is that I can get the probability density in position by integrating over the momentum of the Wigner function. But if you think about it, there are wave functions, and you know about them, the Fock states, right? Which have, sorry, that shouldn't have happened. There are wave functions, right, which have zeros in their probability distribution, right? So these are where you have nodes of the wave function. And what does that mean? That means that that zero, right, has got to be given by an integral over all the momentum values, right? So wherever we have nodes of a wave function, we should expect that we have both positive and negative values. Otherwise, the whole thing is trivial and should be 0 over that whole span, right? So what this means is that if you see, or at least one of the things is that any wave functions that would produce nodes, yeah, should be ones that would have negative values coming from the Wigner function, right? And wave functions with nodes are things that happen for Fock states and happen for higher order states, but they don't just happen for the ground state. It has no nodes, right? And they don't happen if you displace the ground state and things like that. You have to do something special. And usually you have to couple to some sort of quantum degree of freedom. In our case, that's going to be the spin. Yeah. So another final comment to make about these Wigner functions, and here I do just plot a Gaussian distribution, is that if you went and just looked at position and momentum of our Wigner functions, you would find typically that anything displaced from the origin would be rotating around the center with an angular frequency omega. Okay, that's the trap frequency. That is that when you have an oscillator that's in an extreme of position, it then oscillates, or it then gets accelerated towards the origin, at which point it has high momentum but no position, and keeps on sloshing backwards and forwards. So we always work in essentially the interaction picture, yeah. And in the interaction picture, I here called it the rotating frame, if you like. Then any oscillator that's just stably at what, or is stable, it will be just at one position in space, if you like, and it'll stay there. So the basic notion here is that the coordinates that we use are also oscillating round and round in exactly the same as the phase space picture we had before. Yeah? So we track the trivial evolution. The trivial evolution is just the oscillation of the ion in the trap. Okay, the units on this graph, that's the other thing to say, is just what's the distance, if you like, in the real space, so in nanometers, for instance, divided by the units of the 0-point motion, right? So here I had the 0-point motion of 7 nanometers, and so the distance in this phase space is somehow related to real space by this notion here. Okay, so what do we do when we have motional states? Well, one of the typical things we do is we try and learn about them, right? And in fact, that's one of the interesting areas of dealing with oscillators. They've got higher Hilbert spaces, and so you have to think a little bit hard, and you have some freedom to think, how would you like to measure them? So one of the classic measurements that's made is actually to use the anti-Jaynes-Cummings Hamiltonian. So that's this other Hamiltonian, which has this sigma plus, and I've drawn this wrong, I realize, so there should be a dagger here. There should be no dagger there. Okay, so this is the sort of energy non-conserving one where the spin gets excited and so does the oscillator. And the key thing about that is that the matrix elements, as you change the value of n here, the matrix elements of this Hamiltonian, they increase as square root of n, right? So what does that mean? That means if you start with an atom in the ground state, what you should see is just that it gets driven between two states, right? And it'll have a certain Rabi frequency. There will be an oscillation that you see. So indeed, this is what you see here. But actually, if you look carefully, what you'll see is that the oscillations don't quite go to the same depth every time they oscillate, right? And that's an indication that we weren't purely in the ground state. There's a little bit of population indicating that we have some other frequency component in these oscillations. And that's that actually in this case, there's a small probability that the ion didn't start in the ground state, but it started in the n=1 state, where it oscillates a little bit faster. And so that's what we do. We can look at the Fourier components of such a Rabi oscillation, and we see the different weights of the different components, and that tells us what's our population of the different states. And so in this case, we would deduce we had a 97% ground state occupation. In this particular case, yeah, this is data from years ago. So that's got one frequency component, okay, or roughly one frequency component. As I said, there's a slight other frequency component producing our imperfection, if you like. But there's no reason to stop at that point and just make ground states, right? So now that we have these different transitions, one, the carrier, that's this one which just has a sigma plus plus a sigma minus. we have the blue sideband that also acts on the motion. Then if we choose the lengths of these different pulses, then sequences of these can actually be made to achieve arbitrary superpositions of the motional states. And just to give you an idea, one that's very commonly used is you start from the ground state and you make a pi/2 transfer to go to the excited state, right? So I could draw a little bit of different population here. That would be a carrier transition. And then make a pi pulse. So this would be a pi on the blue sideband, or actually the red sideband in this case. Sorry, I should just correct myself, right? This would be this red sideband, the Jaynes-Cummings Hamiltonian. And that thing there produces a superposition of the 0 and the 1 state, right? And then we can diagnose it. We just drive the blue sideband and again look for the Fourier components, right? That's very common. But more arbitrary solutions can, or more complicated pulse sequences can produce arbitrary superpositions of states. One example that I just wanted to show, this is data from the original paper on this from Dave Wineland's group, where actually they've made a superposition of the 0 and 3 Fock states. So 0, this should flop at root 1, if you like. This is the square root of n dependence. And this one here should be at the square root of 4. So you should see two components, one of which oscillates twice as fast as the other. And indeed, that integer relationship is why at some point they completely invert the spin a little later on. Yeah. So this was the first demonstration of this. More recently, NIST have made actually use these techniques to make Fock states going all the way up to n equal to 100 and going superpositions all the way up to 0 plus 18, if you like, right? So they've pushed the control, and this makes you then very sensitive to trap frequency fluctuations. So it's something that's useful for sensing in terms of you get faster averaging down of data if you can make a bigger motional superposition, and 0 plus 18 is certainly a large, what we would call a large motional superposition.
Jonathan, would you mind to take questions now or at the end?
Oh, no, we can do it now. That would be good. Yeah.
So there is basically two questions. One is about the Wigner quasi-probability. Mm-hmm. Can it take values greater than 1, or like normal probability it should be less than 1?
Yeah, it can't take values up to 1. In fact, the largest value it can take is 2 divided by pi. Yeah. Yeah, that's all I can really say. I think I would have to look at the maths as to precisely why that is, but that's what I remember, is that the maximum value is 2 over pi.
Okay, good. I think that's all for the time being. So I think we can move on.
Great. Yeah. One new message I see.
Oh, there's this. Thanks. Yeah.
Oh, okay, good. Yeah. Okay, so I've just told you about lasers, and I sort of indicated earlier on that the only thing you can do is using lasers, but it's not, right? You can also use the electric potentials of the trap to also generate quantum states. And I think it's worth mentioning because actually it's significantly sort of easier not to have to bother with a laser, but also that these states somehow are useful states in the context of a lot of quantum control tasks. So the basic notion is that you can apply on one of the voltages of your trap some oscillating voltage, right? And at the position of the ion, that's likely to produce an electric field, right? So you can imagine, that's what we call it a tickle very often. You can imagine a Hamiltonian term that's got this electric field. It's an energy, so it's proportional to position, and it oscillates at this cosine omega t. Yeah. So again, we go into the interaction picture of this X operator, right? We make it look at the oscillating components, but we can tune this electric field resonant with the oscillation, at which point the remaining Hamiltonian is something which looks like this, right? It's just a constant term in product with the position, essentially, of the atom. So if we turn that into a unitary transformation, we apply it for a certain amount of time, we find that we're exponentiating something which has got A and A dagger terms in it. And that then, it corresponds to what we would call a displacement operator. So what does that do? If you start from an atom in a ground state and apply this displacement, it's like displacing the center of your trap. What you do is you end up with what we would call a coherent state, which is basically the ground state probability distribution or wave function displaced to some position in the phase space. So here is a picture, if you like. You might have started at the origin of phase space, and now what you have is you've displaced by some distance, which in this case would be some IE electric field times T over 2, if you like, if you displaced in position. In fact, what I can see from this is that this is not a displacement in position, but if I was treating this as both, if this is momentum, this is position, then we would see that we've displaced diagonally. So the Hamiltonian there, the basic difference in this case here would be that I should add some additional phase component here, okay? So I can choose the phase of my electric field versus the oscillation phase of my atom, if you like, and that will choose the direction that I make a displacement in this phase space. So then I can apply the same analysis, right? The analysis there was to drive the blue sideband and look what the Rabi oscillations do. And what you see now is that there are many more frequency components present. So if I was to do the Fourier transform of this, you'd find a lot of frequency components. And that produces this classic collapse and revival behavior, which people knew well, if you like, from the, or people always looked for in cavity QED, which is to say that the key to it is that the coherent state has a Poisson distribution of the different Fock states that are involved. Yeah. What does that mean? It means it's got a Poisson sampling, if you like, of the different Rabi frequencies that are involved in creating this spin evolution, right? So what happens to them, because there's a distribution of a certain width, after a certain amount of time, all of the different Rabi frequencies get out of phase with each other, and we get this collapse in the spin population, right? All the different frequency components are not in phase, you stop getting oscillations. But at some point later, when two neighboring components come into sync with each other, then what you'll find is that because this is a fairly, the distribution here, the width of this distribution is not so wide, yeah, then roughly speaking, all of these come back into phase with each other at the same time, and that produces this revival. And it's not to one, and the reason it's not to one, because not all of them come into phase at exactly the same time. Yeah. So this interesting Rabi oscillations, if you like, are indicative of a particular distribution, and this is sort of a well-known behavior for this Poisson type distribution you get from a coherent state. You can also think about making the trap, modulating the trap such as to produce squeeze states. So let me just say how that's done, and then I'll tell you something about the squeeze states, if you like. Here, instead of modulating an electric field, you modulate a quadratic term in your Hamiltonian, right? So same sort of game. There's some sort of cos of omega s times t, but now it's an x squared term that we see here. And now, if you choose the modulation frequency to be twice the trap frequency, then again, into the interaction picture, look for resonant Hamiltonians, you'll find that these Hamiltonians are things with a squared terms or a dagger squared terms, the resonant terms are. And so what does that mean? If we exponentiate such a Hamiltonian, then what we find is an operator here, which is an operator which has got an exponential with a squareds and a dagger squared sitting in the exponential. And what we know about that is that if we apply that to a ground state ion, it generates squeeze states of that ion. So what's a squeeze state? So here's a Wigner function again of one of these squeeze states. And the key thing about it, if you like, is that the width here is, let me call it delta x, I call it delta x squared to be a variance, is given by, if you like, the variance of the ground state, but suppressed by a factor which is e to the minus 2r, where essentially r is equal to the magnitude of this eta t over 4. So it's the argument of this operator up here, right? So what we find is that by applying this squeezing, right, we can reduce the width of the uncertainty in position by a factor which is e to the minus 2r relative to the width that we'd expect to get for the ground state wave function. And the cost we pay, because we have to satisfy Heisenberg, is that this quadrature here, which if you like would be a delta p squared, would be then some sort of P0 squared over 4 times an e to the 2r. It has to get larger, right? And so these two things come together, but one of the nice features is that you can reduce the uncertainty, say, in position. And that's good. If you wanted to, if you had a signal, say, coming from an electric field, which would change the position of the ion, then you're more sensitive to that now because you've got smaller quantum fluctuations of the ion in that direction. And that was sort of motivating, if you like, the guys at NIST to pursue this method. So one thing that you see of this squeezing operator is that it's got a squared terms and it's got a dagger squared terms in it, right? So starting from a ground state, which has no quanta, it's going to produce pairs of quanta, right? So a characteristic thing in this Fock state distribution that you see here, this should be n sitting here, is that it only contains the even terms or even Fock states, right? So that's a key thing about squeeze states. And what these guys at NIST were able to do, sorry, I should just go back, was actually to achieve a 20 dB reduction in the quadrature variance. So that's a factor of 100 in variance. Yeah, that's quite impressive. And they were actually able to do sensing them with a 7 dB gain in their sensitivity due to the fact that they'd used squeeze states. So these are two electronic methods. The one very nice thing about these electronic methods is they allow you to make these Gaussian states. So one of the keys about a squeeze state is that there's no negative Wigner function here. It's not got that sort of special quantum property, if you like, though they're very useful states for sensing and things, yeah? So what you see is that the electric fields or the electric modulation of the trap potential allow you to make states which are Gaussian, right? But have interesting features and high sensitivity, for instance, in this case, because of the squeezing. So let's go back to the laser control. I want to show you another way in which one can generate squeeze states. So this technique is based on what I would call reservoir engineering. So it was actually proposed way back in the 1990s. And then we were lucky enough that it was still lying open to be done in the 2000s, if you like, when I started my research group. And the reservoir engineering in this context, at least, is actually remarkably similar to ground state cooling. So I'm actually showing here exactly the same plot that you saw previously for the ground state cooling, right? It has a combination of this red sideband that in exciting the spin removes a quanta and some dissipation which relaxes the spin. Except that what we did in this experiment was to apply that exact same physics, but in a basis where all of the states here are not anymore the energy eigenstates, but are squeezed energy eigenstates. So you take the Fock state and you apply the squeezing operator to it. So why did we do that? Well, because the interesting thing about that is if you ground state cool in that basis, then your ground state turns out not to be the energy ground state, but it turns out to be a squeeze state of motion, yeah, the one we've just seen previously. So how does that work? Well, you want to find a Hamiltonian that looks like the red sideband, right? And so here is such a Hamiltonian, except that this should be an annihilation operator. In the squeezed basis, right? So op in the squeezed basis. So how do we construct that? Well, one thing we can do is we can just have a look if we can construct it from the original annihilation operator. And so actually what we can do there is if you apply the squeezing operator to the annihilation operator, you'll find that you get a sum of a destruction operator with some weight nu, and another term which has got a creation operator with some weight nu. Yeah. And what that is actually doing is this is actually the operator which now destroys quanta in this squeezed basis. And what's the key now in terms of a laboratory implementation? What do we need to do? We need to make terms which look like an A times sigma plus and also an A dagger times a sigma plus. And so those are two terms that we know already. I've told you about already, if you like. One A sigma plus comes from driving a red sideband. So we have to drive the red sideband with some weight. And an A dagger times sigma plus comes from driving a blue sideband, right? But now we have to drive them together, do the spin excitation together, and we have to make sure there's a good phase relationship between the two. And so what we do there is we apply a 2-frequency laser field. We drive both this transition and this transition simultaneously. And then all of the physics that we did for single Fock states in terms of ground state cooling just gets converted to the same physics, but in now this squeezed basis. So here is the same graph I showed you for ground state cooling, except now what we're probing here is the squeezed sideband in a certain sense, right? What we see is the cooling part. We the exact same Hamiltonian. We get the same physics where we can't drive out of here because we arrived in the ground state. But in this case, it's a squeezed state of motion. So now we can also think about our analysis techniques, right? So this is the analysis we performed before. These are the energy eigenstates. Here's the square root of n dependence. And now if we analyze our squeeze state just with a single sideband drive, we see again some mix of frequency components. And if we look at that distribution in n, we see again, same thing we saw for the NIST experiment, that there are only even occupied states, right? And that's because we've pumped into a squeeze state. But we can also do the same thing I just did, but we play the same trick working on the blue sideband, right? So we engineer here, if you like, something that looks like K plus times sigma plus our K times our sigma minus, but now all in this squeezed basis. So here would be U would be the case of the squeezed basis. In that case, if I've started in the squeeze state, that's my ground state of motion, I should expect to see only one frequency component, exactly as being in the ground state of motion when I did normal sideband cooling. And that's exactly what we saw. We saw, okay, it decays, right? But we saw basically a single frequency component there when we probed in the correct basis, right? And so looking at the population distribution in the squeezed basis then what you see is that we have a high population in the ground state and we have a small contribution from other frequency components. And this immediately allows us to tell you what the fidelity with which we can create the squeeze state was. Okay, so one thing you'll see from that, you'll see in almost every experimental diagram is that it's not perfect, right? And one thing that's not perfect is that you can see this decay envelope that's happening to this quantum state, right? So what is it in trapped ion physics that limits the control of motional states? So there are two things. One we would call motional heating, and it's coming from exactly the same sort of physics that we saw before, right? We have an electric field, which now is not us trying to modulate some voltage on an electrode, but is some noise, right? And I'll come to the sources of noise in a moment. So what's that doing? It's this Hamiltonian that is proportional to position, right? It's shifting noisily around the center of the potential well. And so if it's got a short correlation time, you can go and have a look at a Fermi golden rule type treatment, right? And you find that this here is what we would say is the heating from n equal to 0. I should say 0 to the 1 state, right? And it's given by some factors. So you'll find that the mass is appearing here. It's harder to heat a heavy mass ion, if you like. The trap frequency, because this is telling us how quickly we go in terms of numbers of quanta, right? So the trap frequency also limits that. If you had infinite frequency, you'd have to have a lot of energy to make a jump in number of quanta. But the key component here is actually that there's an electric field, spectral density, evaluated at the trap frequency, right? So you see that it's producing a value omega. So it's essentially asking how much of this noisy field turns up being resonant with the ion, and that will cause the heating. So what are the sources of that? Well, the first one, most common, is that you have technical noise, okay? But if you're working hard, then you should be able to suppress this to what we would say are negligible levels, right? And that's one of the games in a new setup is somehow you start with a certain level of noise, and very often you have to end up going hunting your noise sources to get them down. Another source is that we have resistors around these traps, so Johnson noise can play a role, right? But what we find, if you look at the numbers for that, is that it's much, much too small to explain any of the heating that people see of trapped ions in ion traps. Yeah. So the third candidate is sort of one of the big unknowns in trapped ion physics. Okay, that's what we would call surface noise. Yeah, we think it's some sort of fluctuation charge or sort of dipoles on the surfaces of the electrodes. These are normally gold surfaces, but if you look at a surface carefully, you'll find quite often it's not gold at all. It's got hydrocarbons and things on the top of them. So why do we think these come from the surface? Well, we have evidence that surface treatments can improve these things. We have evidence that cooling down the chips can improve this situation. So we think it's some sort of thermally activated process on the surfaces, but it's one of the things that we really don't understand today. And that's sort of in line with surface physics generally. Surface physics is quite messy and challenging, and I think that's affecting us there. So the one way to get over this is to build a trap where the electrodes are very far from the ion. Yeah, and so that's fine, but actually in the long term, many people would like to make smaller traps for various reasons, getting stronger fields and things like that. So surface noise is one of the big challenges out there in the field today. So this is one source of noise, is motional heating. The other one that I am duty bound to tell you about, it actually limited the experiments on squeezing that I showed, was dephasing, right? So this comes not from the position of the potential well fluctuating in time, but becoming from the curvature fluctuating in time. So if that happens at high frequencies, that can actually parametrically heat the ion, just like the squeezing you saw from the NIST experiment. You can have some sort of squeezing of the ion going on, which excites it up if you have some frequency components at 2 omega. But actually, that's usually completely insignificant in ion trap work. So the more problematic thing is that there is noise, very often technical noise, which affects the frequency of the ion at lower frequencies. And you should think there that the whole bandwidth of frequencies all the way up now affects whether you can track the phase of the ion, because the phase of an oscillator is given by the integral of its frequency all the way from 0 up to time t, right? So what that encompasses is any fluctuation of a very large bandwidth that might have happened to the frequency. And that means you lose the sense of the phase of your oscillator. And since I'm writing in these rotating frames, right, this rotating Wigner functions, if the phase is shifting, then you can imagine that this rotating picture is wobbling backwards and forwards in an uncontrolled way. And so that's going to cause me to lose many of the features that I'd like to draw in these quasi-probability distributions. So I should just say the scaling is such that this effect actually dominates and limits many experiments with large oscillator states, but both dephasing and heating are key causes of problems in the lab.
Jonathan, there are 2 questions. If you would
that's
like
exactly what I wanted to start the question, so that's fine. Yeah.
How do you modulate trap frequency with X-squared term?
That's a good question. Yeah, let me maybe draw it here. Okay. So imagine you have a trap. It's got 3 electrodes. Just for the sake of argument, we'll draw 3 electrodes. And what defines the curvature of this trap? What defines the potential well? Well, it's somehow that there's a voltage on this one. I might produce this one at ground, and there's the same voltage on this one, right? Then halfway between these electrodes, you should find a minimum. And so in order to make sure you modulate the second order term, then you have to modulate both of these ones symmetrically about the ion trap position. Yeah, and that will produce an X-squared term that gets modulated. Yeah.
Okay. Then the other question is, are there regimes where you have to consider more than the spectral density, higher order sort of noise terms?
For the heating, then I don't know of any. That's not to say there aren't regimes, but essentially the ion is a sort of a high Q oscillator. It's got a pretty stable oscillation frequency, and at that point, then it's really the spectral density of the noise which is the governing property, if you like, at that frequency.
Right. So then there is a question which I don't know. Does it depend on the strength of BSB and RSB in order to prepare the squeeze state?
Yeah, let me go back to that. So in this picture here, what you'll see is that the thing that defines the squeezing, if you like, I wish I could get rid of all of these things. The squeezing is defined now, right, by this operator here, which produces me a sum of two terms. And actually the amount of squeezing is given by the ratio of the strengths of these two terms. So what happens in this case is that the ratio of the strength of the red and blue sideband determines how much squeezing you have, but actually the absolute strength of them doesn't matter. Yeah, so it's fairly robust in the sense you can have fluctuations in your laser power, but as long as the ratio of these red and blue sidebands stays the same, then you're still good. Yeah.
Okay, then the last one is, in case of unresolved sideband, is it possible to cool down?
It's possible to cool down. You've seen a little bit about that in D.D. Liveread's talk when he talks about EIT cooling. So what you do need in order to cool is you need a heavier weight of driving transitions on some resonance that reduces quanta versus anything that increases quanta. So there are ways of making sure you don't get any excitations on a blue sideband by, in EIT cooling, putting a zero of your internal state structure on top of it. But typically what will happen is that if you don't perfectly eliminate these off-resonant processes, then you will cool down for sure, but you won't get as cold as you would. You won't get to the ground state, for instance. So one situation, you know that Doppler cooling works. You've seen that in an earlier lecture, if you like. That's the unresolved limit of cooling, typically. And to make it easy to go to low temperatures near the ground state, it's typically the case that you want to go into this resolved sideband limit.
Okay, I think that's all for the moment.
Okay, great. How far through are we? I feel like I'm slower than I expected. That's all I was wondering.
No, you still have half an hour.
Yeah, so I'm going slower than I expected. Okay. Good. Okay, so I'll write less probably. And yes, anyway, let's see. Good. So the next thing I wanted to talk about was actually a different type of control, which comes from what we call state-dependent forces. And it's most commonly being used to make what we call Schrödinger cat states. So these Schrödinger cat states, well, you know about cats, right? So you have an alive cat. It's in a box with an atom that can decay randomly. And what happens is that box should release a vial of poison and you get then a dead cat. But if you didn't open the box and you didn't have any information about what's inside the box, you end up in a situation where you've got correlations between whether the atom decayed and whether the cat is alive. And what that means is that you should strictly be writing down a superposition of an atom in an excited state and a cat being alive, and an atom in a ground state and the cat being dead. Okay, so there's an entangled state between the spin, which is a microscopic system, and the cat, which is, surely we agree it's a macroscopic system in general, right? So how can we get Hamiltonians that generate states that look a little bit like a cat? One of the ways is to drive actually equally the red and blue sidebands. So if we do that, we get the Hamiltonian showed here. We just sum up the two Hamiltonians we had before, red sideband and blue sideband. And now we have a position operator that I've called x, and it's multiplied with a sigma x operator acting on the spin. So what does that do? It's proportional. This is a Hamiltonian that's proportional to position. I exponentiate that, I get a displacement operator, which is proportional, or which has an amplitude proportional to the amount of time actually that I've applied it for, but now is proportional to whether I'm in a plus or a minus eigenstate of sigma x. So if I start off in a superposition of eigenstates of sigma x, that's position, for instance, being in the spin up state, then on applying this Hamiltonian, what I'm going to do is I'm going to push the position of the atom either to being at plus x if I'm in the left pointing state, or to being at minus x if I'm in the right pointing state. In fact, these are coherent states, so they're oscillating states, but they're fully out of phase with each other, correlated with the state of the spin. So I can write my state, if you like, as atom pointing right or left, correlated with whether I'm in a negative coherent state or a positive coherent state. And that's my analogy to a cat. Why? Because this coherent state can be something that's large. I can make it in principle, I could make it a meter, right? And so the size of coherent state is something that can be reconciled with the classical regime. And that's why we make the analogy then to something something macroscopic that's like a cat, though of course this is the motion of a microscopic particle. Yeah. So how does this look? If we apply such a state-dependent force to an oscillator, so we make a transition from the atom being in the spin-up state, which is a superposition of left and right, to being correlated with some external degree of freedom. And what that's going to do is that if we applied a small or no displacement, we expect if we measure whether we're in spin-up, we expect always to find the answer 1. That's this state here. Once we've become entangled with another degree of freedom, on measuring spin-up, we'll find we've got an equal probability to be either in the up state or in the down state, right? That's what's happening here. And what you see is 3 different cases here, which I've chosen, and they correspond to different starting states, okay? And the different starting states, let's first start with the blue one. This is what happens when we just apply that procedure to a ground state. And so what you see here is an indication that there's a drop in coherence, and this is an indication of the size of the ground state, the RMS extent, because as these wave packets start to separate from each other and lose overlap with each other, you get this loss of coherence because there's now entanglement between the spin and the motion. Now, if you do that on a squeeze state, and you do it on the narrow axis of a squeeze state, then what you see is this curve where there's a drop which is much now faster than we had before, right? The overlap is lost much quicker than before. And if you do it on the long axis of a squeeze state, you see the overlap takes a longer time to drop. Yeah. So this is indicative, or this is the starting point of a notion that here, if we did this sort of drive, we create a cat which is really just coherent states. But if we see this faster drop, i.e. we started with a squeeze state and then applied this state-dependent force, as I call it, we should expect that these are now squeezed Schrödinger cat states. These are superpositions of wave packets, which both of them are now squeezed wave packets. So how big are these cats, right? What's the state of the art today? The state of the art is that the biggest ones that we've been able to make are around 240 nanometers. And one of the things you can ask, and it's sort of the relationship back to the cat, right, is how distinguishable is this state from this state here, right? So one measure of that is how, what's the overlap of a state sitting over here to a state sitting over here. And you see that these overlaps are really tiny, right? They're very distinct states in space now, and that's a function of the fact that there's a reasonably large extent of this cat, and that's sort of the boundary, probing the boundary of the macroscopicity, if you like. For the squeezed cats, it's even more extreme, right? You get some sort of factor of 10 to the minus 500. These are clearly extremely distinguishable. Yeah. So how quantum is this, and can we go further than that? Well, one of the things to go further than that, one of the frustrations, if you like, of this sort of state is that you measure the spin, right? And when the spin is entangled with the motion, you don't really find out a lot about the motional state that way. You just find out that the spin was entangled with something, right? So how can we find more out about the motion? Well, we can go back to the detection that we had before. So the spin that I'm talking about here is on this S1/2 to D5/2 transition. And if we perform detection, what we do is we scatter a lot of photons if we started off in the S1/2 state, right? And if we scatter a lot of photons, we'll receive them on our camera and our ion will be bright, yeah? The problem with that from the point of view of the oscillator is that we have to recoil thousands of photons in order to make a good bright detection, okay? So it completely shreds our oscillator state. But we also have the case where we started in the up state here, yeah? And if we started in the up state, we won't scatter any photons. There's no recoil. And we get, if you like, an ideal back action projection of the quantum measurement without having any adverse physical characteristics. So if we perform a measurement, we detect for a certain amount of time, and we don't see any photons, we can then after that go and look and do some sort of examination. What's the quantum state of our system? So what we find, if we measure in the spin up, spin down case, right, is that we can post-select on getting a dark intermediate measurement, and then we can do the right things to create the Wigner function, right? And here's a picture of the Wigner function that we see here. And what you see, it's got a superposition of two Gaussian states at two different positions. That's these blobs here. But in the middle, what you see are these stark interference fringes between the two, where the Wigner function is going from plus values to minus values. That's the blue that you see here, right? So this is a very strong indication that this is really a quantum state that couldn't have been produced or has sort of this extra essence of having nodes in the wave function, and it's really an archetypal quantum state. We call this a Schrödinger cat state. Just to connect that back to what we saw earlier, okay? So when we don't do any post-selection, then what we have is a situation where we would find that our oscillator state, if we were just to look at the oscillator and cross out the spin, is entangled with the spin. And so we actually have a mixture of being in the minus coherent state and in the plus state. And if we look at Rabi oscillations on the blue sideband, then we see this collapse and revival that you saw before, and it's a Poisson distribution in the state distribution, right? These are the different Fock states that we have occupied. After this measurement, though, if we post-select on seeing up, then we now have an equal superposition of being in alpha and minus alpha, but they've got a definite phase relationship between the two. And what that means is that in the Fock state distribution, all the even Fock states, sorry, I think this must be the, yeah, this should say all the odd Fock states should disappear. Clearly, I got this the wrong way around, right? And basically, just through the point of view of not scattering photons, you see that all of the alternate populations have been deleted, and now you only have even populations, right? Now, the distances between these peaks is twice as far, if you like, so there's a larger frequency separation between the Rabi frequencies, and what you find there is you get an additional revival at about half the time because they come back into phase quicker with each other. We do the other one, if you like, post-select on a different state. We see that the other Fock states go to 0, if you like, and we end up again with this evens, or only these alternate populations being occupied. So that's, I think I'm going to skip that actually. I just wanted to say then that one of the key things is to be able to see the fringes. And the fringes are given by somehow the symmetry of the state. And I should just say that the largest state that we ever made and can actually see some fringes in the middle, and this is a picture of a perfect state, not the state that we actually made, has this distance of 240 nanometers. So this was what it would look like if we made the Wigner function. I would never be able to persuade my students to do that because it would require really a lot of data taking to take such a Wigner function. Okay, so I very quickly, I'm trying to think what to talk about now. Yeah, I'm not going to discuss error correction in any detail because it's a bit complicated. I just wanted to point out that this concept of squeezing and Schrödinger cat states, if you like, can be applied to more complicated states. So the same procedure of applying a state-dependent force and making a projected measurement, if repeated, and in particular repeated on squeeze states, can produce these superpositions of squeeze states that then have this rather interesting periodic structure, both in the position direction and in the momentum direction. Yeah, so if we look at the wave functions of these, we'll see these are periodic states. And what was cool for me was that actually these turn out to be an error correction code for quantum computing. Yeah. And we were able to do experiments there. I really don't have time, I think, to go into all of the details of that because I need to tell you about multi-ion states. But just to say that here's some signals. Again, the same trace that you've seen before in terms of when you saw this decay down to 50%, we were then applying it to the ground state or to a squeeze state. Now we're applying it to these periodic states. And you see that in addition to it decaying, and it would decay, you can see a decay something like this, there's some structure due to the periodicity of the initial state in there. And actually these states are exactly made up so that you can build a qubit this way. So at a particular distance, which reflects the periodicity of the states, you see that if the state is centered at the origin, you get a peak. But if this state has been shifted to the side, and you'll see that that's looking like the same distribution shifted to the side, you get a dip, yeah? And this is indicative of the fact that actually that's a qubit. This is the measurement of a qubit. And what I have is that if this whole distribution is at one point, I get the plus state of the qubit. If the whole distribution is at another point, it's a minus state. Now, here actually is an operator that's twice as long, but this is what we use to check for errors in this qubit. This is an error correcting code, yeah? And what you see is that regardless of the qubit state, this one is always producing the same value, right? So that's saying that the information about errors, we call it a stabilizer operator, is independent or roughly independent of the state of the qubit. So I'm going to flick through this stuff. There's a lot of stuff we did with that, but I don't want to have time to talk about it. Just to say that in the last year, we were able to perform quantum error correction for the first time in this system. And what we see of our logical state, if you like, we look at the Pauli observables of our logical state. We see that if we don't do correction, we get fast decay. But if we perform correction, then we can extend the length of a lifetime of our logical qubit. And we extend it by actually a factor of 3.5 sort of thing. So I think that's the biggest extension of any logical coherent qubit that anyone was able to perform to date. Okay, so that was a little too quick, but I hope you got an overview for the fact that these cat states can be produced and that multi-component cat states are sort of interesting in their own right for quantum computing. To finish up, I just wanted to talk about what happens when we have more than one ion. So as I explained at the beginning, then when you have more than one ion, they have a Coulomb interaction between them, right? And when there's two, you can think of that as a little spring connecting the two. But this also extends up to having long chains. So this is a chain of 50 ions. And now, if you like, if any one of these ions moves, all of the others feel the impact of that motion. So how should we think about that? There's two ways we can think about it. And I think one you dealt with D.D. Leibfried was to think about static normal modes of the system. Of course, when you have coupled pendula, this is kind of first year classical physics, right? That you can resolve this into normal modes, which if you set a normal mode going, it oscillates at a given frequency, right? So that's a picture we typically use when we've got quantum gates and when the couplings are strong. But the other thing we can actually have is a situation in which the ions, they sit near each other by a distance d. Let's imagine they've got the same frequency. And we can think instead of the normal mode picture about thinking about a dynamical evolution. Imagine that you put energy into just this ion. You'd expect that ion through the coupling to slosh backwards and forwards with some regular period. Yeah, we would call that the exchange time or exchange frequency. And it's got this dependence, and it depends in 1 over the distance cubed. I just want you to remember that. Yeah. So we can consider that as a Hamiltonian that couples these local potentials, right? And indeed, here's the multiplier is this exchange frequency, and it creates and annihilates the quanta in the two different wells. They trade off against each other in an energy-preserving way. So how can we view this dynamic picture in terms of the normal modes? I'm sure you're familiar with this with classical physics, but it's basically that we have these two types of motion, one where the ions oscillate in phase with each other, one where they oscillate out of phase with each other. And what you would see is that the difference of frequency of these two is basically given by this exchange frequency. Yeah, so this is what produces the dynamical evolution in this picture, is just the separation in frequencies of the normal modes in this picture. So how does that look for many more ions? So here I'm going to plot frequencies, if you like, of 10 ions, beryllium ions, where I imagine that I've got my trap set up so that radially it's an ion string, and perpendicular to that string direction, I've got trap frequencies of 13 and 14 megahertz. And what I'm going to do is show two plots, which are different frequencies along the axis of the trap. So what do you see? In this case where you've got a low frequency well along the axis, what does that mean? It means two things. It means the curvature is not very high, but it also means that the ions are well separated from each other, right? D is large and the exchange frequency is small. What does that mean? It means there's a bundle of modes sitting down at the bottom. These are actually all the axial modes of oscillation. But further up, there's this bundle of radial modes. And actually, what tells you about the separation of these is the exchange frequency. And that was given by 1 over d cubed, which is the distance between the ions, set by the axial trap frequency. And it's got a factor which is proportional to 1 over the frequency of the radial modes, which is this 13 megahertz. So now let's turn up the axial trap frequency. Yeah, we push the ions closer together. And what you see is that, again, the axial modes look like a pretty regularly spaced array, but now the radial modes start to expand, the exchange frequency increased, and they actually all start to merge with each other, even between the two sets of modes in the two different directions. So what's setting the splitting here is this exchange frequency. And depending on the distance between the ions, then you can say to yourself, well, the dynamics from that will be at a high frequency if I produced ions that are close together, or at a low frequency compared to maybe my control timescale if the ions are relatively far apart. And so these two complementary pictures are useful. So I just wanted to point out a couple of nice experiments in that regard. This was from the group in Osaka, Kenji Toyoda and colleagues, where they have really two ions each in a radial potential, and they consider this hopping term, that's this kappa, as this exchange between the two ions. Now, the oscillations are bosons, right? So what this is, and the type of Hamiltonian that I showed you, sorry about that, here is a beam splitter type Hamiltonian, right? So what can they do here? They can start the system off with a quanta in each well, and they will interact according to the beam splitter. And what you'll find is that there's bunching. Both ions will, or the quanta will either go to the same ion, right? But you don't know which of the same ion which of the ions they go to. But you end up in a situation where they never come out of the beam splitter in different ports. And that they were able to demonstrate, right, for phonons for mechanical motion, right? So here they have phonon coincidence rates looking at this time here, and you'll see that the coincidence goes down to 0 at the particular time when the beam splitter should have happened. Yeah. Just one nice example, they're extending this physics to doing things which also involve driving with the Jaynes-Cummings Hamiltonian, and that has a sort of many-body name, if you like, a Jaynes-Cummings-Hubble model, which has got some interesting regimes to study for many-body physics. The other thing that can be done, and this work was done at NIST in 2011, was to create really two potentials for the two ions and be able to control them independently. And this is a very nice illustration, if you like. The reason they can do this is by making small ion traps and putting the ions fairly close to the chip. Yeah. So beware the heating, right? And here they saw exactly the correspondence that I was telling you about earlier. Here's the dynamical evolution of a quantum hopping between the two different ions in the two different potential wells. The slope here is given by the heating, because their heating is high because the chip is relatively small. So that's something they have to improve. And then in the spectroscopy domain, this is when the two ions are on resonance with each other. You can look at what the frequencies of motion are. And these are the two normal modes, which are now split, you'll see, by a few kilohertz, reflective of the timescale that you see here, rather than maybe the splittings we might use in quantum computing, which would be on the sort of megahertz level. Yeah. And this is saying that this dynamical behavior now is slower than, say, control timescales of lasers, which allows you to be in a different regime of looking at hopping of bosons between different sites. So just to say that that's got a longer term future that's of interest, and I'll come back to in the next lecture if you like. So one can imagine trying to make electrode structures so one can make 2D arrays of ions. And in this case, this is a hexagonal lattice, which is really defined by the structure of the underlying electrodes. So again, I remind you that the hopping timescale is the distance between ions, and the height is somehow the thing that's challenging with respect to noise, because that governs the heating that we see. And people have really mapped this out to see whether this is really feasible. And I plot a graph here, not for you to read, and I won't go through it in any detail. So the theoretical studies have been performed, and people are working in this direction. There's sort of new results coming from, I think, NIST at the moment on this. But again, going back to the big problem, if you like, the heating problem will be somehow critical to making this work in a larger scale. But that's the path, if you like, of motional states towards many-body control and examining many-body physics. So with that, then I'd like to thank you for your attention. I thank my group who backed me up and provide nice experimental results that hopefully some of them I could show you, and look forward to further questions then. Yeah.
Thanks, Jonathan. I think there is already one question that's on the chat. Could could you produce cat states with 2 ions?
Yeah, so I mean, in a certain sense, then you'll see that in the quantum logic gates that we do on two ions to entangle 2 spins. That in a sense, what's happening there is there's at that time there's usually some set of spin configuration which is correlated with being in the ground state still, some which is correlated with being in a plus coherent state, some correlated with being in a minus coherent state. So in a sense, that's a cat state, but it's not this 2-component cat that we talked about. Yeah, and there may be more flexibility there with projecting out motional states. So I would say maybe the thing to do there would not be to look so much at cat states, but to look at more complex states that you could create if you had the additional flexibility of having 2 spins. Yeah, so that would somehow, it would be more like looking at these GKP, these multi-component squeeze states that I would find attractive about a 2-ion realization. Yeah.
All right. Are there any other questions that might, please write it down on the chat box. I don't see any at the moment. So, okay, if that is not the case, maybe we close this session now. Thanks for your, this is a wonderful talk. I enjoyed it. Yeah.
Okay.
And we would continue, I think it's tomorrow. Oh, no, it's Monday. Yeah. Right.
Yes.
So,
You got a week.
Right. So have a nice weekend for you.
Indeed, and you. Yeah. Bye.
Yeah. Okay. Take care. Bye.
Yeah.
Thank you, Manoj. The next talk will be at 8 o'clock Indian time. So till then, there is a break.
Okay.